everyone, am I audible? Good evening, everyone. Am I audible? Okay. Thank you, Aradhya. So let's wait for 5 more minutes so that everyone can join, and then we'll start this last week session. Okay. let's start this session. Okay, so welcome you all in the last week of these live sessions for the course of Introduction to Machine Learning instructed by Professor Balaraman sir from IIT Madras. So today we are going to study about the theoretical part of machine learning along with the third paradigm, that is reinforcement learning. Actually, we have started with the concept of machine learning, which extends to the three dimensions or three paradigms: supervised, unsupervised and reinforcement, where we have specifically majorly we have focused on supervised study, and from the last 2 weeks we are studying about unsupervised method include clustering. So now this is the last week and we will be seeing what the third paradigm is, that is reinforcement learning. Actually, reinforcement learning is somehow different from what we have studied till now. So it comes into strategic intelligence also. So there is a full you can say a course for reinforcement learning and deep reinforcement learning. So we will be seeing how these reinforcement learning can be applied, or how is it different from simple supervised or unsupervised approach. So we will be seeing its introduction in this session. Before that, because this branch, machine learning or deep learning, is typically a sub branch of mathematics and statistics. Okay, so and we are talking a lot about data, probability, marginal probabilities, and these error functions. So actually there is something that is actual present, and we are predicting something through this study of machine learning. So how close we are to this actual data or actual distribution, this is actually we are going to see in this theoretical part of machine learning. So I am not going to go deeper in the theory part, but this is very important for those who wants to study the machine learning in mathematical terms. Okay, so presently much of the work is shifted towards deep learning, which is one of the algorithm of machine learning, which includes neural networks and deep neural networks, but the actual core study is the same. Okay, so in this study we will be seeing some VC dimension, what is VC dimension, how to calculate it. So somehow I am going to give this idea. Alright, so let's start. So the introduction to theory in machine learning, it means the term we are going to use here is theory. Okay, so in computer science, theory often refers to some problems of hardness. It means how difficult a problem to solve. Okay, so do you heard this term Turing machine? Yes or no? Turing machine.
Yes, ma'am.
Right, so it's a theoretical model, right? It's established way back before, which helps you to formulate that how the problem goes flow, yeah, how the flow of the problem is, so that we can solve any problem using machine, right? So why this come into picture? Because we wanted to know that any problem that is given to this system or mathematics, how difficult is it to solve, right? So theory comes from this perspective, first thing. Second is what we have learned in data structures. I mean, if you belong to this computer science learning, so this is the very basic steps of space and time complexity, where if you remember, we have some C codes and we say that okay, what is the time complexity, what is the space complexity. It means how much space the particular program will take from the memory, how much time it will take to complete run, right? So for example, generally you have dealt with these problems with sorting algorithms. There are insertion sort, selection sort, and bubble sort, and merge sort, and other types of sorting algorithms are there. So the time complexity of particular algorithm is n square. Here it is order of n. It means how much time it will take to converge, right? So sometimes we need those programs or those models which are quick to go. We need we have some time constraints. Secondly, sometimes we have some space constraints. So presently, uh, much of the work is shifted towards GPUs, right? So the CPU processing is not very sufficient for modeling such big models in machine learning and deep learning. So it means the space is also a constraint, time is also a constraint. So here also we can go towards the theory. Let's say we are developing two models for data, okay. So which is the best one? You can say okay, this model 1 is taking less time than the model 2. So it means we can say that by theoretically proven from this time complexity of model 1 and model 2, model 1 is quicker and faster, that's why we can adopt it. Okay, third is approximability. So basically, generally some problems are NP hard, right, or NP complete. So what are those problems? So as you know, there are some problems which are polynomial time solvable. So it means those if I give you some amount of data and have some problem and it can be solved in polynomial time, then good to go, okay, no problem. If I give you a problem of addition of two numbers, it's okay, you can solve it in polynomial time, no problem. But there are some problems which cannot be solved in polynomial time, so they are called NP problems, right, non-polynomial time problems. So let's say, and some problems are there which cannot be solved, okay, in polynomial or non-polynomial time, we don't know. So those are called NP hard problems. And some subset of problems are there where we can say, okay, we can't solve it, but we can solve some of the instances, we can approximate it. So for example, this traveling salesman problem. So what is traveling salesman problem? A salesman is there, he has to visit some cities. So the constraint is he has to visit the city only once. He should not go to the city again, and he has to traverse all the cities in less time. So you have shortest path, okay. So in the less time, traveling salesman problem is there. So it's not possible to solve, right. So there is no perfect solution for it. But if we have some graph, if we have some nodes, we can approximate it somehow for some of the instances. That's why they are called as NP complete problems. So this is also the part of theoretical computer science, where we are learning about the problem, where we are learning about the paradigms theoretically based on mathematics. How to solve them, what observations can you provide there. So similarly here also in machine learning, because it's also a branch from statistics or mathematics, we have to apply some theoretical frameworks to machine learning. So some question arises, okay. So according to this, we can ask a question that how hard is to approximate a solution. Why I am calling it approximation? Because you don't know the actual output, okay. So let's say I want to develop a model which can simply count the number of leaves in a plant, okay. So it's a very hard problem. So I can have, let's say, so what I can do, I can say okay, I can't go towards this problem, let's assume something, okay. So let's restrict our study. So I can say let's start with some plants. So I started with radish plant and I want to count the number of leaves, okay. Now you have restricted over a plant. But plant has different types of backgrounds, different types of leaves at different stages. Maybe it's in a pot, maybe some branches are occluded. So there are multiple challenges there. So if you have some type of data and you create one good machine learning algorithm to count the number of leaves, it may be that you are not providing the whole data present in the world, you are just giving a sample data, right. So it means you don't know what the actual distribution is, but you are somehow approximating it. So that's why the question here written is, how hard is to approximate a solution? You don't know the solution. If you know the solution, why do you go towards this machine learning, okay. So you are just predicting something for future. So if I want to predict the weather of tomorrow, so how approximate, how close I am towards this solution. So this modeling of this solution, this approximating of solution, how hard it is. Second, how do we measure this hardness? We can say this hard, this is difficult, this is easy. How can you say, in mathematics and in computer science also, we work towards quantification. We don't know anything about quality. Quality, maybe some of you will say ki, okay, this quick sort is very hard to learn. Okay, some of you know it by heart and say, no ma'am, it's a very easy algorithm, I can just write it in 5 minutes, no worries for it. So this hardness is actually debatable. So what we can do is we quantify some methods to measure this hardness, and on the basis of that measures we can say that this one is good and the other one is not. Okay, so in this scenario we can somehow say that there is something called generalization error which we want. Okay, so these terms, when it emerges, there are two particular things that you should keep in mind while thinking about this theoretical concept. First is real data. It means actual. It can be anything. Okay, so real, actual, journal. It means all the data in this world which you have seen or not seen, it doesn't matter. It means the actual thing that is present, but as a human we don't have that understanding. So second is your sample, or you can say your trainable. So the data set that you collect is trainable. It means that is called, I am taking it as D, sample data or trainable data, but that is only a sub part of the actual big amount of data that is present in the world. So if I say you have to work on human faces, so if you collect the faces from India, it will be different. If you collect the faces from Europe, it will be different. Even in India, if you go towards south, you have some different structure of the faces. If you will go towards northeast, you have some different structure of the faces. So basically we actually don't have this understanding that how much variety of data is present there. Okay, but according to the knowledge, we just somehow gather the data and we are trying to make it more generalizable. Okay, so what we wanted is, we wanted the generalization error to be minimized. Now what is generalization error? So generalization error is represented with this E, small e, okay, and this H means hypothesis. So basically when we started to learn machine learning with mathematical perspectives, we started to coin the terms in mathematics only. So hypothesis means you can refer the hypothesis as models for your understanding right now. Okay, so any model that you are creating is one hypothesis. So for example, you have learned about that linear regression. Okay, so in linear regression we define betas, those learning parameters. So let's say I have beta I for a model M, for first linear regression model. For same linear regression model, I have some beta j which are slightly different from it. So this can be hypothesis 1 and this can be hypothesis 2. So it means that anyhow from the hypothesis I am getting the predictions, I am getting the output. Okay, so what is this generalization error is? Probability that hypothesis H makes a mistake on new data point sampled from distribution D. So what they are saying is, first they are saying there is some distribution. It means this distribution means the actual data which you don't know. This is unknown to you and you will never know about it. Any problem in machine learning, any problem in your real life, you don't know about this D, because you can't have the knowledge of actual thing that is present in this world. We are just dependent on the knowledge that we have. Okay, so let's say you have some knowledge, you are very interested in physics, in astronomy, you get to know, okay, sun's environment is like this, moon's environment is like this. So because you have read a lot of literature, you have that knowledge. For you that knowledge is the whole world, but it is not the actual thing that is actually present in the real world, right? So many mysteries of the world we don't know. So in the same way, this main distribution D, which we say in mathematics, we say there is a true distribution D which we don't know. So from this true distribution, if I take one sample, okay, so let's stick to this example where we have to process a human face. Okay, so for this human face I have to predict the age. So predicting the age from all over the planet, not even this planet, if there are humans anywhere in this whole universe, I pick those points, I give that point to the hypothesis, and the probability that hypothesis will make mistake on that point will be my generalization error. So why I am saying generalization error? Because I am coining this term with respect to probability. So what is the chance that if your model is ready, if your hypothesis is ready, and what is the chance that it will make a mistake is called generalization error. So this we can't know, but this is what we want to achieve. This so when we start processing any literature, when we are working towards any theory, so in theory there is like as we say dunya gol hai, it means this earth is round, a big assumption, right? So this is to be true, which we have from the way back we assume it, okay, but some of the things are not very easy, right? So we don't know about it. So similarly we wanted this generalization error to be minimized, but we don't know anything about it. First, we don't know about the distribution. We have hypothesis, okay, that is trained on some portion of the data, but we don't know about the distribution. If you don't know about the distribution, then obviously you can't have this probability. Okay, no problem. So now next term is coined as empirical error. So this empirical error, because we are saying that we don't know about actual distribution, we don't know about the whole data. So if you don't know about the whole, let's work on the samples. So let's say you can't have the information of the every human present on this, let's say in this earth, on this earth, let's not go towards any other thing, but you can't have that information also. Okay, so what we can say that, okay, we have some countries, let's pick some of the sample data out of those countries. So that sample data may have the same distribution as the actual data. We are assuming it. So that's why the other term is coined as empirical error. So this empirical error is the error measured on training data. That's why you have training data, that's why they are not talking in probabilities, they are talking about the measured point of view. It means let's say you have m samples, okay, m is equal to 1000, you have 1000 samples. So for all those 1000 samples you have a hypothesis. So check if that hypothesis is giving you the correct answer or not. So this is your hypothesis answer, this is your correct answer. So if they don't match, then they will be counted as error. Okay, so that's why it is written as 1. So it's more like a perceptron thing. Okay, if the hypothesis or model outputs is not matching the true output, then 1. If second output is not matched, 2. Third output is not matched, 4. So somehow you are increasing this error. So from how many samples are correctly classified or how many are incorrectly classified. So this incorrection is empirical error, and you know it. We have data, we have hypothesis, so we can know about this. So challenge is estimate this generalization error using empirical error. So now we will talk in terms of statistics or mathematics, because in statistics also, when we have this population, we have how the statistics start is when we wanted to have some generalization over some population. So that population, any problem? So I was talking about statistical generalization, where we wanted to generalize over a population. So we wanted to know what distribution the population is following. So because we don't have that, we choose some data and we make some assumptions, and then we generalize it over the populations. Okay. So similarly, there are some concept of agriculture and probabilities. So because this is also similar problem of actual distribution and the sampled error, so that's why we will use statistics and probability for it. So major challenges, we want to achieve this, but because we don't have information regarding this, then we will use this to approximate this. Okay, so we are going to estimate generalization error using empirical error. So that's why word estimate is there. Why I am focusing on these words also in the today's class, because look, if you are in academics and if you are going towards research, then these words actually matters a lot. Okay, so where you want to use the word measure, where you want to use the word estimate, where the probability should be there, where the distribution should be there, where the population should be there, should be very restricted. Okay, these are not the words that we can use vaguely anywhere. Alright, so that's why just observe here that how these words are also written. So towards this challenge, let's go towards empirical risk minimization. So because we don't have the information of generalization error, we have the information of empirical error. So we will be going towards empirical risk minimization, means risk is error. Okay, so most the learning algorithms aim to minimize empirical error. Till now, what you have learned in supervised approach. So I am strictly following here supervised approach. I am not talking anything about unsupervised. Why? Because I just don't remember the book from where you can follow this. It's a very, very popular book. I just forgot the name of the author. When he first starting to discover this theoretical machine learning, he is completely restricted his study to supervised approach, because when we know something, we can estimate, right? So if we are, because this unsupervised approach is more or less towards the pattern mining or data analysis part. Okay, so it is more towards how similarity you are defining, how losses you are defining, it depends on you. But here the goal is actually very clear, because you know the output. So I want my input to match my output, that's it, nothing else, nothing more. So for that, I want to make some model which can directly maps this x to y relationship. Okay, and that relationship is not known to me. So that's why we are talking about this error minimization or risk minimization for supervised approaches. So till now, the linear regression problem, the classification problems, SVM, and those decision trees, KNN, neural network, all of them, all those learning algorithms aim to minimize this error, right? So what we were doing is, we were using those gradient information, we were using MLEs, maximum likelihood estimation, which is the opposite part of this risk minimization. Okay, so what we were trying to do, that we were trying to either minimize the error of the training data or maximize the probability of the training data. So we are always working on training data, and that data is very important. Okay, so now question arises, let's say I have one hypothesis H1, one hypothesis H2, which models my data x to y, which models my data x to y. How will you say that this is good or this is good? Okay, so that's what I want to achieve, right? So it's more like what statistics do is ki, we have, that's a separate part, how to create those hypotheses. The part here is which will help you to minimize this error, right? So what we are doing, that we have multiple iterations in perceptron, we have multiple iterations in neural network using back propagation. What we are doing is we are minimizing it. Okay, that's why I told you if a model with beta i's and the same model with beta j's, can be called as two different hypotheses. Okay, so from hypothesis 1 we can jump to hypothesis 2 using some minimization optimization, right? So that's why here it is written that this error, okay, this is your empirical error for hypothesis, let's say for beta I, you can just think about it. So this is a model with beta i's, and there are multiple similar models in capital H. So it means capital H means all the betas, let's say. So it is not restricted, okay, it is not restricted that let's say ki this beta I for linear regression, this beta j is for linear regression. No, this hypothesis, that's why it's more generalized term. It contains all the models which are good or bad, you don't know, but just that those models, from those models you can give your input and some output will be given to you. That output can be good, that output can be bad. So we have to think about that which hypothesis is best for you. So that's why which hypothesis is best for me, which will give me the minimum empirical error, because we know the training data. Okay, so that's why for this terminology we will say this capital H as hypothesis class, small h as simple hypothesis that belongs to this class. That's why this big hypothesis H can be like let's say linear regression model. Okay, so here the internal hypothesis will be the weights for those particular linear regression model, or we can have this hypothesis classes as a SVM class. Okay, so all the weights inside contains these other hypotheses which constitutes in this class. Okay, so basically what I wanted to know that from this hypothesis class, from this type of modeling, we wanted to get these weights or these parameters out of the the system, which will helps you to minimize the error. So this is your generally what the algorithms are doing. So what algorithms are doing, they are reducing your empirical error, right? So here when they have started to work on, they have used choose classifiers. They are not working on regression problems, they have started this theory on classification. Okay, so that's why they are saying the linear classifiers are defined by parameter theta. Some theta parameters are there. So for example, neural these are the hypotheses. That's why it is written hypothesis class H can be linear classifiers, neural network. Okay, so in which some architecture and weights are there. So how these are defined, how these are dependent on, it's another topic. Ultimately the question is what we have studied till now is defined by this equation. Okay, so practical issue is this empirical risk minimizer may not find the true minimizer due to optimization challenges. This is also because sometimes your optimization parameters are not set so that it can let's say this is your function. So we wanted to move here, but it stuck here. So it means this is local optima. So somehow due to some optimization challenges, or one optimization challenge we have studied in SVM, that is quadratic programming. Okay, it's very difficult. So due to some optimization challenges, we can say that somehow the model is trying to learn what is given in the data, but it cannot be called as true minimizer. In other words, I can say that there is a student who tries to learn mathematics, and what he started with, he said okay, there are 3 particular books on which the mathematics questions are there. So what he has done, he has taken all these 3 books and he has either solved them or crammed them by heart. It's just that if any problem is given by that book, that student is able to solve it, okay, with good accuracy. I'll not say 100%, but yeah, good accuracy. But there are not, those 3 books do not contain every problem of mathematics, right? So let's say there are multiple problems given to that student in the real life which are not related or not present in that book. So here may not be the true good accuracy, may not provide good accuracy over those problems. Okay, so that's why this is the major issue. That's why we are learning towards this theoretical concept, that how to reach the global minima, how to reach the actual generalization error. So for that we will be using 2 types of theoretical tools, 2 types of properties, first and second. Okay, one of you has asked me that that कि ma'am, is these lectures or these videos are sufficient for particular examination. So look, I don't know about your main examination, but what I it's just that according to a my understanding, the examination will be based on your obviously syllabus, and your syllabus is based on those video lectures provided by the official video lectures. Okay, the these topics which I am covering is from those lectures, but it does not cover the whole concept. Okay, maybe some of the things I may have missed. I have also some restrictions 1 week in a week, so maybe I have left out. So just go through all the video lectures basically. Secondly, what I have found out from your assignments, so if you have also observed that these small topics, if they have given to you na, ki let's say ki this theoretical tool is important, this theoretical tool is important, so maybe they can ask 1 or 2 questions from this theoretical tool only. Okay, so it's very simple. Okay, it's a very simple theoretical tool, like for example union bound, you all know about it actually. So let's say ki there are three events, A1, A2 and A3. Okay, so I want to calculate the probability of A1 union A2 union A3. Okay, these are your this one. So I want to calculate this union probability, right? So it's a simple formula, you know it from the Venn diagram also, that it is like PA1 plus PA2 plus PA3, if you know. Okay, you add this, then you subtract PA1 intersection A2, PA2 intersection A3 and PA1 intersection A3, and add PA1 intersection A2 intersection A3. Do you know this or not? This formula, simple formula of three events A1, A2 and A3. If I want to calculate the probability of PA1 union A2 union A3, so it's more like that. I wanted this probability, this probability, this probability and these three plus this fourth one. Okay, so this is what I want. So when I am adding this A1, A2, A3, it repeating this the intersection also. That's why I am subtracting it, and at final end I am adding this small portion which is covered by all these three. So do you know this formula, yes or no? अगर आपको ये याद नहीं है तो ये तो याद होगा ही होगा.
Yes, ma'am. Of course, I learned this formula.
Right, so means this probability na is when we have started learning in our 11th 12th standard, it's quite simple. It was very interesting to solve. Okay, the question is ki, let's say I have let's say I have 10 balls in the bag and I want to pick out the 2, so what is the probability 2 by 10? So it's very simple, it's very easy to learn about this A1 A2. Okay, set Venn diagram. But as you go with K levels, N levels, then it's quite difficult to understand. Okay, so we are not able to generalize it. So that's why here comes this complexity of probability, that now these formulas comes into picture. It is the same thing which is written here. So what they are saying, the union probability of the union of some events should be less than equal to the summation of those probability. Why? You can see here, this A1, A2, A3, I am writing it as equal, right? So it means something is subtracting from these three, addition of these three. If something is subtracting there, then obviously this term is bigger than this term. So that's why we are writing as this union is less than summation. So union means the probability of the union of events. Summation means summation of the probabilities. Just look about this P, placement of P here and this placement of P. Okay, so this is a very simple formula. This is called union bound. So you are bounding the union. So generally in theoretical machine learning or reinforcement learning or game theories or these type of studies, major study is about bound. Okay, bound means you have some variable, you have some, maybe let's say measure, that is probability or some error or something, you want to bound it. So bound it means you have to bound it like this. So it is less than something and greater than something. So the upper bound and the lower bounds. So here I am bounding it using this principle, which is a simple principle okay, of probability. So here it's a simple theoretical tool which you all know. So maybe some question will be asked, maybe means I don't know anything about your examination, but what I have found out from your assignments, that's what I am putting an observation. Some questions are asked on basis of this simple union bound, and you have gone through all the lectures, you know that where it is used, but there you got confused. Okay, so this is how things can be asked in examination as well. Okay, so while reading or while preparing these small things, please take into your observation. All right, so first rule is simple, that is the probability of any union event is less than the summation of all individual probabilities. Okay, second is Hopkins inequality. So there is one inequality where they are saying that for IID Bernoulli random variables. So why they are calling as Bernoulli? Bernoulli means the either the output is 1 or 0. Okay. So that's why, look here, this Bernoulli is written. So this is a type of distribution. So they are saying this Hopkins inequality for IID means identical and independent. It means there is a bag, let's say, generally when you will write about this probabilistic measures also, many times you have to use this word IID. Without this, the definitions are incomplete. Why? First I means independent. So let's say you have a bag and you have some objects inside that bag, and I ask you to pick one object out of the bag by closing your eye. So it means that any of the object you can pick. So it means one of the object is not dependent on another. So that's why it is independent. Second is identical. It means the probability of choosing one object out of the bag is equal to the probability of another, right? So let's say you have a dice to throw. So you have 6 numbers out of it. So all those 6 numbers have equal probability. Means you can have 1 also, 2 also, 3 also, 4 also, 5 or 6, anything. Let's say that that dice is biased. It means it is somehow has some rough surface towards 6. So it means now it is not identical. Somehow when you will throw it, it will be biased towards some numbers. So now these are not identical. Okay. So these are independent. Identical means we are not making any dependence between those objects, those random variables. Secondly, all have equal probability. So they are saying if there are some random variables z1 to zm, m is the number, and you have to pick, you know, these Bernoulli random variables, and you know about the mean of them. So the mean is phi. So let's say the probability of phi cap minus phi is greater than gamma is bounded by this equation. So what does it means? Basically same concept of empirical and actual error, okay, comes into this statistical concepts. So we have found out this equation and we can use this equation here, that's why it is written. So let's say this is the actual mean. Okay, this phi is your actual mean, this is there, so it means this is your, let me just erase it all. So this is your generalization error, E of h. Okay, this is your empirical error. Okay, this is your predicted error. So the difference between them should be greater than gamma. So gamma is a very small quantity, that is your tolerance. You can say that ki, okay, theek hai, we know the both errors and it should not be greater than, let's say, 0.01. Okay, so I am making this giving you this tolerance. So I want to calculate the probability that aside this tolerance, I can tolerate the difference of error by 0.01, but if it is greater than 0.01, then what is its probability? That's what I wanted to know. दोबारा सुनना कि what is this means? This is the probability that your error is high. Error is high means here the error is means difference between true and empirical. It means that you have empirical error and you know about, let's say you know about generalization error, and I don't want the difference to be very high, so I want to calculate the probability that what is the probability the error is so high. So that's why the greater than sign is there. So they actually use this inequality as a bound, that they are bounding it that if the error is greater than gamma, it should be less than this. So this is your upper bound. Okay, so you can have an understanding. Let's say this probability is 0.8. Okay, so it is less than 0.8. It means that the chances of this difference is so high is less than 0.8. It means the less the number will be, it means you are bounding it. Okay, now I have the relaxation. Let's say the number is 0.1. So I am saying that the chances of this error is less than 0.1. It means you will say that okay, 0.1 से तो ज़्यादा नहीं है. I am having a good model with me. Okay, so this is what I want to know. So that's why using this bound and using this inequality, we are going to map our original problem. Our problem was that we have empirical error and we want to estimate this. Okay, so ultimately we don't want to estimate that. We want to estimate this difference to be negligible, right? So that's why, because we don't have any formula, we don't have any means to calculate the true error, generalization error, true distribution. So we can't go towards that end. So that's why they are using it in upside down way, that let's not estimate that error, let's estimate this difference. So if I can get this difference by this probabilistic measure, then I can say that my this empirical error is actually a good estimate for it. Okay, so now we will use these two things in our situation. So same thing what we have written there, phi cap minus phi greater than gamma. Okay, this phi cap minus phi cap greater than gamma less than this. Okay, so here I am just using my terms of generalization error and empirical error here and here. So what they have written, just look, probability of, this is your empirical error, this is your generalization error, taking the mod same as there, greater than gamma same as there. Okay, so this is what we have created. Okay, but because empirical error will be belonging to some hypothesis, so that's why I have written here for some hypothesis belong to H. So this is how they actually write their papers, their equations, their formulas. So this is a way, complete pure mathematical way. So these are mathematical guys, so they will be giving you a lot of symbols here, and every symbol is must and necessary. If you will remove that, you can even change the actual meaning of this equation. So that's why statistics, and if we are learning machine learning in the perception of statistics, then we should be knowing that these symbols are also very important. Okay, so it means that if we are talking about some H, so it means they are giving there, writing here for some H, it means it is actually there exists. There exists a H in a capital H where the minimization error, this error will be giving you this concept. So this concept is same. So here they have written, what they have written, 2e minus 2 gamma square m. Okay, so they are also writing it here like, let's move further, maybe you can have more. Have I not given this equation in an easy way? this one, this. So this is the same thing which I wanted you to see, that your goal is to bound this. Okay, this is your empirical error and this is your true error. So because it is in this absolute thing, you can write it vice versa also. So in the starting one you have written it like this. Okay, so it doesn't matter whether you write it like this or write it like this, it doesn't matter. Okay, so what they are writing, that this for 1h, okay, it should be less than equal to this formula. It's as simple as this, 2e this one. So now you will ask that from where I can get this k, what is this k? So this k, we will be seeing that where we are going to have this k. I have written it somewhere, maybe. Have I not given you this? Maybe I forget. Okay. So basically this k means number of hypotheses. Okay, so that's why this union comes into picture. Okay, so why we are look, we wanted from Hovding's inequality, we are saying this E of h minus E of h greater than gamma, the probability should be less than equal to 2e minus gamma square m. Okay, this is from Hovding's inequality, simple. But what I am saying, that this formula is fitted for hypothesis h, and I have multiple hypotheses. Any doubt? Okay, so this is for single h, and I have h1, h2, h3 till hk. Okay, let's say I am bounding this for k hypothesis. I know that if there are k hypotheses in my capital H class. So similarly, I have a probability for h1, probability for h2, probability for h3, probability for h4, and probability for hk. Okay, so now using the upper bound, using this bound, union bound, we can say that the union of all, union of all this probability for h1, for h2, for h3 should be less than equal to summation, right? And it is also in the less than part. So that's why when we are submitting it, taking a summation, so it means the variable here is constant, right? So it will going to be summed by k times, because we have k hypothesis. So that's why it is written here as k. And it is written, I think the summation is written here like this. Okay, so this summation means this is k times. So that's why submitting it over k, this k comes here and other things are written exactly like this, 2e to the power minus 2 gamma square m. So is this equation clear or not? Let me know this first. Is this equation clear or not? Let me know this first.
Clear, ma'am.
Okay, so it means that now we have this equation which is giving you high error. This is high error. Okay, so basically I wanted that this convergence. Okay, so from this I have this equation, and I am saying you that with probability greater than 1 minus delta, it means I am associating this probability as 1 minus delta, which I want to calculate. So how we are going to estimate it? Let's say your delta is this right hand side part, this one. This right hand side part I am giving it as delta, I am assuming it as delta. So this is basically this delta represent the failure probability. Why? Because I am saying you this is the high error is less than equal to 2 ke minus 2 gamma square m. So this is your high error. So I am giving I am asking you that let's say this error is delta. So this delta is the failure probability. Okay, so this delta is failure probability. Let's solve this. So when you solve this delta, what you will do is this is minus e to the power, right? So to have it into positive side, I just take it into the reverse side, right? So if I take it to the reverse side, take delta here. So you got this equation, okay? And to solve this, how to solve this exponential? Taking log both sides. So log of e is simply 1, okay? So it is nothing. So basically when I am taking the log, then this power comes here, and taking log here, the log value comes here. So I want to calculate this gamma. So the gamma value is this. So basically what you can observe here, gamma, k, delta and m. If you know this, your problem is solved. You don't have any issue. So basically either in some question they will give you k, they will give you delta, they will give you m, and they ask you for gamma, or vice versa. They can give you any of them, and using this formula you have to calculate the fourth one that is not known to you. So basically what are these? So first is k. K is number of hypotheses. There are maybe 100 hypotheses in the class, or 1000 hypotheses in the class. M is the number of samples. So generally you always heard like for machine learning, for deep learning, you need large amount of data, you need large amount of data. What is this large amount? How much? 1k, 2k, 1 million, 2 million, how many, right? So basically in statistics, in probability, using the concept of probability also, we can estimate the minimum number of data samples. Ki, okay, these many samples should be there with you to estimate these type of mean, okay? Or in the other words, we can say that if you have this much amount of data, then you can approach towards the global mean, the true mean. So that's why you need this much amount of data. So how much amount of data is needed? You can have this information from M. Now this delta is the probability of failure. So the probability of success will be 1 minus delta, okay? And this gamma is your tolerance. So how much error is tolerable to you? So higher the tolerance will be, obviously the difference, if the difference is higher, you are saying it means your system is not good. If the tolerance is less, it means you are approaching towards the true mean, okay? So that's how this bound is very important. So I think there is one question also, yes. So basically that's what I told you, right? So this is your gamma. If you want to calculate m also, you can somehow juggle it up and calculate the value of m. So here they are calculating the value of m from this formula. So it's just that just don't misuse this symbol, okay? So where you are using 1 minus, at least take care that how this greater than and less than are changing, okay? So it means you are not solving a equation, you are solving an inequality, okay? So here also some example is given. Let's say k is given to you, delta is given to you, gamma is given to you, you have to calculate m. So m should be greater than equal to these many number of samples. So maybe some question can be asked like how much minimum, how many samples do you require for a let's say 1000 hypothesis, if the tolerance is this and the probability of success or probability of failure is this, okay? So now you have to be knowing that you have to use this formula, put the variables in the correct form and calculate it simply, okay? So this is how these things are easy to go to estimate that how many data points are better, how this tolerance, how it affects with the data point increase or decrease. Okay, so they have given one observation also, that small h means this low k, it means if we have less amount of hypothesis, it means low sample complexity but high bias. It means that let us say we do not have many models, okay, it means I am saying k is very low, let us say 2 or 3. So, it means I am testing, you can treat it as you have only 2 or 3 iterations. So, in 2 or 3 iterations, it means your model is very simple. If your model is simple, it means it is moving towards high bias. But if your k is very large, let us say you have a large number of iterations, it means your model has more complexity. So, it means that high variance, it is moving towards high variance. So, as the k is high, variance is high, as the k is low, bias is high or variance is low. Okay, so you can associate this, the value of k in terms of variance. So, when you have less amount of hypothesis, it means you have less models to check, it means the model will be simple, the answer will be simple, and simple means high bias. In the other case, the model will be complex, obviously the bias will be low and variance will be high, so it will be moving towards overfitting. So, that is how we can choose that how many iterations should be there, from how many steps we can count, how many data points are necessary, what is the tolerance limit should be there. Okay. So, this is how this concept of generalizing error can help you to estimate that from your data is it good or not. Okay. Is it clear to you, yes or no? Can we go ahead?
Yes, ma'am.
Thank you. So, next topic is VC dimension. So, VC dimension is given by this scientist Vapnik and Chernyshevsky. So, that is why it is called a VC dimension. Then what is it? It is a measure of the capacity of a statistical classification model, specifically in the terms of its ability to shatter data sets. So, basically it is more like that. It is also one of the measures which can helps you to define this this hardness of a problem to be solved, how to approximate whether it is hard or not. So, this term shatter we associate with VC dimension. First we will see what is this shatter, then we will come towards the definition again. So, basically first thing that hypothesis space, that is capital H. So, this is a set of all possible functions or classifiers that a model can learn. For example, in linear classifier, all the possible straight line that can divide the space into two classes. So, that is what I have told you. So, this H belongs, let us say in this H there are H1, H2, H3 and many more. So, maybe it is line like this, it is a line like this, it is a line like this. So, it means if I am saying you this H is from 2D line space, then any line from 2D space belongs to this H. So, that line is a linear classifier and we can associate any line in this. So, that is how we work towards SVM, how we are getting that hyperplane, that is also a 2D line. From all the spaces we are getting one hyperplane, right. So, it means that from big hypothesis H, we are choosing one of the best line that can divide your data into two parts, right, two or more parts, let us say. So, if it is a linear classifier in two parts. So, that is why this is your hypothesis space in which there are multiple hypotheses are there. And they are saying that if space is written, it means set of all possible functions. So, they are saying all the possible lines that we can associate with this linear classifier is in this set. So, first thing is hypothesis set. Second thing is the term shattering. So, shattering means a hypothesis space shatters a set of points, this word shatters here, shatters a set of points if it can correctly classify all possible labelings of those points. So, what I wanted to say you, let us say hypothesis space means any line, any 2D line, okay. So, now I am talking about space. So, let us say a single line and I have a set of points. So, let us say I have let's say I have 2 points, okay. So, I have 2 points and binary classification. So, point number A, point number B. So if I draw this line, it can classify them in class 1 or class 2. Okay, so let's say there are 4 possibilities for A and B to belong any class. So how this possibility comes? A, B, 1, 0, 0, 1, 0, 0, 1, 1. It means possibility is whether they belong to the same class or they belong to the different class. So if they belong to different class A and B, the line can be here and it can simply divide it, simple, no problem. If they belong to same class, then I can say like AB like here, no problem. So it means that this line is able to classify correctly these 2 points for any combination. Any combination means this A can be 1, B can, means all the possible combination that you can have. So this is a one set of points, right? The set of point, how many points are there? There are 2 points. So it means these 2D lines are able to shatter 2 set of points. So their VC dimension will be 2. Okay. Now talk about 3 points. Let's say we have A, B and C. So let's say A, B, C are all in 3 in the same class. So same class, we can go towards that. It means the line can divide it. But what happens if these 2 are in same class, this is in different? Okay, so somehow we have to think about that whether this line is able for all the configuration in this space. So ultimately what I wanted you to say that let's say this is the space and I am having any ABC points, any ABC points anywhere. So can a simple line is able to classify them correctly, yes or no? We don't know the classification, so we have to make sure for any set of classes. It means A can be in class 1, B can be in class 0, C can be in class 1, means any combination can a line can separate it. If yes, then it means it shatters. If no, it means it doesn't shatter. Is that clear to you, the meaning of shattering?
Hello.
Hello,
Hello.
hello, hello,
Yes,
hello.
ma'am. Can
Is
you,
it?
ma'am, please explain the settling again? Actually, due to some network problem, I'm not getting all the points you explained.
It's okay. Let's go towards this again. I am giving you one example, okay? So let's say what shattering means. Just think about it. First thing is it is talking about hypothesis space. So if I am telling you the hypothesis space is a 2D line space, it means all the 2D line, any 2D line, first thing is. So is if any 2D line and you have a set of points. So set of points means you can have 2 set of points, 3 set of points, 4 set of points. We started one single set of point. It actually, this is the way to solve these questions. Okay. So how we start with? We start with 1D, then go towards higher dimension. So let's start with one set of points. So set of points. So first we fix hypothesis. This is your 2D space, 2D line. First we fix this. Okay. Next is set of points. So set is 1, 2, 3. You can go towards like this. Now you have one set of point means let's say I have 1 point, this A. So how many combination we can have for A? Either 0 or 1. Okay. So let's say, and the placement on this 2D space. So anywhere A can be present. Let's say A is here and it belongs to 0 class. I can have line like this. I can have line like this. There are multiple lines. I can simply classify it. Above this line 0, below this line 1, or above this line 1, below this line 0, anything, only one point is there. Okay. So it means this 2D line space, that means this hypothesis H shatters A, no problem. It is able to classify A correctly, whether it is 0 or 1, all combinations. Now we will go towards 2 set of points. 2 means let's say we have 2 points A and B. Okay. So now A and B, let's draw them. So this A and B can be found anywhere. So let's say these are found like this. So they can be like here. So how many combination can be there? Either A or B in same class or different class. So if they are in different class, one line can be here. If they are in same class, one line can be here. So it means that this 2D line can shatter 2 set of points also. For binary, I am talking about only binary classification, not more than that. Okay. So it's a concept that they have defined for binary classification. So for A and B, any 2 points over this space can be correctly classified, चाहे कुछ भी उनकी classes हो, any combination of classes they have, whether 0 0, whether 1 1, 1 0 or 1 1, it doesn't matter. If there are 2 points, we can classify, no problem. Now go towards 3. Okay, no problem. Let's go towards 3. So, and alternatively think about a scenario where it cannot shatter, then it will help you more. Okay, so let's say I have 3, this A, B and C. So there will be like either these two are in the same class, or these two are means 2 of them are in the same class and 1 in the different. I can simply cut it out, no problem. Any combination, I can simply use 2D data with 3 points, no problem, no, not at all problem. Question is now with 4 points. So let's say these are the 4 points, and if 3 of them are in single class, no problem, this we can do the shattering easily. How? Here we can draw the line. Okay, no problem. Lekin if these are two are in one class, second are in another, we can do like this. Okay, but what I am telling you, for every possible combination it should shatter. What if this belongs to class 1, this belongs to class 1, and this belongs to class 0, and this belongs to class 0? Can any 2D line separate, single 2D line can separate these classes, yes or no?
No.
No. So it means that these are 4 set of points, right? So it does not shatter, it does not classify. So it means that this 2D line, this set of hypotheses with 2D lines can shatter only 3 set of points. So how to say this? So this is very long statement to say. So we say that the VC dimension of this hypothesis class is 3. So this VC dimension of hypothesis class is maximum number of points that can be shattered by this hypothesis class. So maximum point, how many points it can shatter? 3. So it means the VC dimension is 3. Getting my point? Is it clear how to check this VC dimension thing?
Yes, ma'am.
Okay, so maybe I have more questions, let's see them. So this is the same questions. So let's say one hypothesis is linear classifier in 2D. It means you have only these things. So if you have case of 3, you will means you have 3 points, you will have 8 cases. So you have to be chosen those 8 cases. Just think about the worst scenario where it can't shatter. If you can't think about it, it means it is shattering, right? So similarly, if we have 4, like we have drawn here, so it means this 2D classifier has maximum 3 shattering points. So it means its VC dimension is 3. Another look, this is the example 2. So now hypothesis is intervals on real line. So how the interval look like? Interval means A comma B. Okay, so it means you will say that if the point lies between A and B, then it class is 1, otherwise 0. Okay, so let me ask you that the answer is written here. So let me ask you that if this point A is here, can it be shattered using this hypothesis? Because it is on the real line, that's why I have drawn this real line. Okay, this is your real line. So it means if this class A belongs to 0, then your A comma B will be here somehow. I should not say A, it is P. If this class belongs to 0, then my A comma B will be here, somehow here. So it means this classifier will be good. If this belongs to class 1, then my A comma B will be here. Okay, it means that you can classify this point P with the help of this one interval. If you define one interval, any of that interval anyone from this hypothesis H can be used to shatter this single point P, yes or no? Is it clear, yes or no?
Yes, ma'am.
ठीक है. Now move towards next set of points. So next set of points means set number 2. It means I have 2 points P and Q. So I have 2 points P and Q. Let's say they both belongs to same class. Okay. And another case is where they both belong to different class. So how it can be? If they belong to same class 1, then the interval can be here, and if they belongs to different class, it means the interval can be here, because inside this interval the class is 1, it can be like this, 1 inside the interval, 1 outside the interval. Okay. Another case can be P inside the interval, Q outside. और सेम क्लास में दूसरा एक केस हो सकता है आपका जहाँ पर आपका दोनों ही इंटरवल से बाहर है. It means here both the classes has label 1 1, here it is 0 0, this is 0, this is 1, and this is 1 and this is 0. Or fold combination using this single interval we can use it. Yes or no?
Yes.
Okay. Now can you tell me about the point 3? Can I do this for 3? Which case it will affect? So if I have 3 points P, Q and R, which combination will it not shatter? Because the answer is written here 2. Obviously it will not shatter. So if this P belongs to 1, this also belongs to 1, but it belongs to 0. So where you will make this interval? How can you make this? Because if you are going to make this in interval, this will left. If you make this here, this will left. If you make this here, you can't make an interval which will make P and R to be in same class. Okay. Especially in 1. Look. Now I want to tell you one more thing. This is 1 0 1 and this is 0 1 0. This can be shattered. You can write the interval here. Okay. This can be shattered because inside it is 1, outside it is 0. But this cannot be shattered. So it means that there is one combination with 3 set of points where this intervals hypothesis is not going to shatter them, is not going to classify them. That's why the VC dimension is 2 for this class. Is that clear? Any doubt in this VC dimension?
No, ma'am.
Okay. So now why this VC dimension matters? So a model with very high VC dimension may fit the training data well but fail to generalize it. It means that let's say I am having one VC dimension of some hypothesis is very high, right? Let's say it is it may be good with let's say 48 dimension of data. It is good. So it means that I can also infer by this case that it is well fitting on the training data, but maybe some generalizability issue. Okay. So basically from this VC dimension also, from this the value of VC dimension, it also helps to calculate the sample complexity. So how to get the sample complexity, that it will tell you how much data we need to learn. It's a simple same case as we have seen how to calculate M. So for a hypothesis class with VC dimension D, the number of training samples N required for good generalization grows roughly like this. Okay. Why? Because generally it is very difficult to calculate VC dimensions because we are not able to see that if it is going to be shattered all the points or not. Okay, it's easy to say for these lines or this simple thing means just think about it. Can you think about if I am going to say let's say some set of hypothesis is able to shatter 6 D points. Can you imagine that how these points can be placed, or you can't think of every scenario. Okay, so that's why we need some data on which we can test it on. Okay, so we need some placement of points. So I am giving you this placement that you can put it like this. It's easy to think, but let's say if we increase the number of points, how will you place in this 2D set? Okay, I can't have that information. So that's why some sample complexity is calculated using this VC dimension that we know beforehand. Okay, so it's more like that. Now there is a term called pack learning. So it's a very important term if if you move towards the theoretical machine learning. What it means is probably approximately correct, pack. It's a learning that it's a formal framework that helps you to understand when and how well a machine learning algorithm can learn a concept from data. It means it's more like in ML what we are actually doing, we are mining some pattern. So this pattern mining is actually learning a concept. So how well it is learning from the concept is given in this definition of pack learning. So the main crux idea is any concept or any hypothesis is pack learnable if with a high probability the learner can find a hypothesis that is approximately correct using the reasonable amount of data and computation. It's very difficult to understand. So let's understand it by breaking it out step by step. So first is probably approximately correct. What is this? It means probably, this is the same terminology that we can use it for our formula that we have seen, right? So we have seen delta, K, M and gamma, right? So probably means 1 minus delta. It means probability of success. So the learning algorithm should succeed with high probability. It means this 1 minus delta should be very high. 1 minus delta is high means delta should be low. Okay. Second is approximately. Approximately, this means error. So the hypothesis should be close to true concept. It means that this error, this is greater than gamma. It means they are talking about gamma. So approximation means this gamma. So this gamma should be low. So and correct means refers to how well the model generalize on unseen data. It means it should not be used just on the training data, but also about the generalizability concept. So that's why we wanted to know that with this low tolerance can we achieve high success or not. So if some hypothesis is achieving this success with high probability, then we can call it as pack learnable. So how we can say that the hypothesis H is pack learnable? Why? Because we have, first thing, we have a hypothesis H class in which we have some concept to target, that is C. It means there are multiple hypotheses. Okay, so we have to choose one. Okay, so distribution over D you don't know. There is one epsilon, this epsilon is error tolerance. This is also called gamma. You can say that gamma. And this is confidence. So this is the error, the probability of error, your probability of failure. So this is your confidence. So if there exists an algorithm, if there exists an hypothesis that can, with probability at least 1 minus delta, can find an hypothesis such that this occurs, it is the same concept. Okay, it's the same concept, then we can say that the number of samples required is 1 minus epsilon. Number of samples required is polynomial in 1 minus epsilon, 1 minus delta, and the size of hypothesis class. So basically what they wanted to tell you, that they are saying कि for some hypothesis which we are testing, we are saying it as pack learnable if with high probability and low tolerance or either we can say that with low tolerance the probability of success is very high. So if it is like that, you have to bound it these success probabilities. Okay, so if I am saying 95% chance with success, you are saying that the tolerance is 0.0001, it means it is pack learnable. So I am defining all these things. Okay, I am defining delta, I am defining epsilon. So for some h, if I am defining these terms, if it is coming under these restrictions, then it's good, it is pack learnable, otherwise not. So you have to define these bounds. So if I in the other way I can say that if some model is giving you 95% accuracy with small amount of error, okay, then it is pack learnable. If some model is not giving you, then it is not pack learnable over these parameters. So these parameters are very important because we don't know which is, you know, which is very high or which is very low. High, low we don't know, so we have to define it. If I am saying that if my model is pack learnable over 75%, then it's good to go. I have to define this delta. No one has the liberty to control this, so it means that if you are defining pack learnable, you have to define what is epsilon, what is delta, you have to give beforehand. Okay, so that's why it is written as at least. So it is another concept to say the same equation that we have studied here, this equation, this one. So same equation is there. So it is also saying ki less than something, we are also saying less than delta ultimately. So these concepts are quite similar. So generally from the last side of experiments, I have simple questions actually. Yeah, you have simple question, we see dimension of 2D space, or it means it's a simple questions, not much is asking you for the last. Okay, so this is what is given you in the theoretical form of machine learning. If you have any doubt, then go for it. Otherwise, we will be going towards this reinforcement learning. So reinforcement learning is not given in detail in your syllabus. So it's a small concept that we will clear it today, and you can simply go for, because it's in very raw state in your syllabus. Okay, so if you have any questions, then go for it. Otherwise, we'll start reinforcement learning.
You can start the next topic now.
Okay, thank you so much. So now reinforcement learning, it's a type of machine learning, it's one of the paradigm of machine learning along with supervised and unsupervised. So it's a type where an agent learn by interacting with its environment. So basically when we start the concept of learning, we start with okay, how students learn with the help of supervisor, that's why supervision is there. Now they say that if no one is around, what can we do? Okay, it means no one is going to supervise you, it is unsupervised. But question arises, how human learns? Either human learn in supervised state or unsupervised state. So they say that human don't learn typically by supervision, but they learn by themselves. So what they how they learn, how, you know, how our brain work, if you have thought about like this. Let's say you are working towards an examination. Okay, let's say this is your introduction to machine learning, there is nothing you know, no supervisor is given to you, you are preparing by yourself. So what you will do, you start preparing it because you have some data. Okay, some data is given to you, some concepts are given to you, you start learning. Now what you will do, you take some step, you take a step, you learn something, and you had given one quiz, first quiz. That quiz has given you some feedback. Okay, you have not performed well. Okay, all right. So I'm not talking about you know by knowing the answer or by not knowing the answers. It's not about supervision or unsupervision. It's completely independent of that. It's just that you got a feedback. You got a feedback that okay, from this step as I am taking, this is not a good way to learn. I have to improve myself. Then how to improve yourself? This is another task. So to improve yourself, you start looking videos. So let's say you start looking videos, then give the exams. You again didn't score well. You say, okay, videos are not the good option. Okay, so now what you are doing, you start learning from the literature, books. But when you start reading from the books, you got good marks. So it means that you have a concept now in your mind, that I'll read from books. I'll not go through the videos, I'll read from books. Or from the multiple videos, you start following some channels. Okay, so let's say you start following first channel, your friend recommended you, but you didn't get good marks from that channel. You learned well, but you didn't get good marks. It means you are not able to generalize it. So you go for the next channel. Someone is giving you more, maybe more information, you are more comfortable, you are more understandable for that topic. And now it's your system that in your brain, that from that feedback you get it like, okay, this channel is good for me. This is what some feedbacks is reinforcing you to learn. Okay, the first channel that you have saw, it's good, your friend is getting good marks, but for you something is reinforcing you. That feedbacks from the quiz are reinforcing you to change your strategy. Okay, so that's why it is called reinforcement. And there is, every time the agent is there, it means this agent, why we call it as, because we get this concept from human, so that's why this agent can be treated as human or the model, you can say. So it means the model or some mind is there to take decisions. Okay, so this agent learns by interacting with its environment. So how you are interacting with your environment? You are giving quiz every time. In human life, when we, let's say, take an example of dog. So what it, if you throw one disc to the dog, what it do is, you motivate the dog to go and grab it. So when it grab it and take it to you, you pat on the dog's head, and it looks like to him that you are giving good feedback. Okay, good, very good. If your teacher say that good, very good, these words motivates you. So this motivation is somehow the type of reinforcement. But as I already told you in the starting of this lecture, we have to quantify it, right? So using trial and error method, we are getting some feedback. So we are having some feedback in the form of rewards or punishment. So if there is a reward, then it's +1, punishment -1. So let's say you are playing a game. Okay, so when you start, if you know chess or any game you start to play, you don't know anything about it, right? You start playing it. Okay, you play one time, you play second time, you play third time. Now your mind is trained for some moves that you will say, no, we will not move towards this. For example, a simple game Ludo or Snake and Ladder, we all play it, right? So how we say that, okay, Snake and Ladder, let's say it's a single process game, you have to do what the dice say. But let's say you have Ludo, you have at least 4 possibilities, right? Which move you have to make, right? So after some times, after playing with some good person, having good rewards, good punishments are also good for it. Okay, so if you say, if this moves makes you lose the game, you will not try not to repeat it. So this is how reinforcement learning works. So it's neither supervised not unsupervised, it's more like something is reinforcing you to learn, right? Let's say see some key comparisons. So in supervised, the label data is given to you, okay, input and output. In unsupervised, no data, no clear data is given to you. In reinforcement, you are not told the right answer. आपको answers पता होंगे, but it is not given to you that this is the only right answer, because in life, in human life, multiple choices are there at multiple instances and all have some reward. So for example, let's say I want to eat in a restaurant, okay, so I like to eat ice cream maybe, but today I am having cold. So there are other options of sweets, okay, so something is reinforcing me to take my decisions. So it's more like a decision power, a decision making can be achieved with the help of these reinforcement learning. So and another example can be, this can be very useful for medical data. So how the medical thing goes on, like for example, you have some problem, you have headache or fever, you went to a doctor. Okay, so what doctor gives you? Doctor checks you up and gives you one medicine. Okay, after that medicine, the doctor tell you take this medicine for 3 days and come back to me. After 3 days, the doctor is seeing your feedback for this medicine, if it is good to go or not, whether you have some more actions to do or not. So maybe that medicine is not good for you, it is maybe some allergies are surfing out from those medicines. So what the doctor will do, it will change the medicine. So from those feedback, the decisions are tend to reinforce. Okay, so here in reinforcement, we interact with the environment, try some actions, observe some outcomes. So from those outcomes, there either can be rewards or punishments. It can be like there cannot, it may not be direct reward. For example, if you are playing chess, okay, or if you are playing ludo, so when the first die you throw, you start with your whatever you call it as object, you start playing, right? You move this this thing from here to here. Okay, the first chance, this will not decide whether you are going to win or not, right? So it means that there can be, it can, like the major goal is to get it at home. Okay, so it may be some percentage of reward is given to you, but it can be a punishment also. Okay, so it can lead to punishment, it can lead to reward. This is not direct. At this stage we can't say it very directly. Okay, so in supervised, the model learns to map input to output, x to y, and in unsupervised we try to mine patterns. Here learning is driven by experience, not direct supervision. So that's what I am saying, that some reinforcement is there. So for example, an illustrative example is bicycle riding. So it is not supervised, no one can exact give you instruction that just put your foot here, move your paddle in with this speed, only this degree. No, you don't do it. It is not unsupervised, you don't just watch people to ride and figure it out, okay, let's do it. No, it's not like that. It can be like you can mine some pattern while seeing someone riding, and you can have an idea that okay, this is the bicycle handles, we have to sit like this, we have to hold the handles like this, we have to make pedals like this, but still you can't able to learn it. It's reinforcement. When you try, you fall, learn to fall, you get some feedback, okay, I don't have to push the pedal in this speed, I don't have to move myself like this, I have to sit like this. So this is how your mind is making up while getting some reward. So if you get a very clean push of your bicycle, then you say that okay, now I have learned it. So this is how this reinforcement learning is human driven. So this feedback is trial and error basically. So reinforcement learning agent, that we call it as RL agent, tries different actions. So basically it's more like state space game. So there is some state S1, you take some action and move to state S2. So it's more like, just think always about a game. So you have some, let's say tic-tac-toe, I have put it here. Okay, so next state, taking some action, let's say next action is like here. Okay, so now I have to move this to here. This action will lead to moving this, from moving this to this place. So this is how different actions are taken. These are the different states. So it learns which action leads to better outcomes. So that's why when you are playing chess or when you are playing these online games, it suggests you you can choose this move, you can move toward this place. Okay, so the delayed nature of rewards add complexity. So as I told you, like if you are having a ludo, okay, if you place your dime like this, here to here, so because it is delaying your rewards, maybe if you are moving towards like this and you stuck here, and okay, so the delayed nature of rewards adds complexity, because sometimes the rewards get delayed and it adds more complexity, because it can lead to negative punishment, negative rewards or punishment, it can lead to more positive ones, you may not know. So you might get feedback while the action that is caused. After the action, what can be the possible states, what can be the possible whether you are going to win, whether you are going to lose. So this is how trial and error is the key to this reinforcement learning. So this is one experiment that where this RL originated. Some psychologists have used this experiment. Like what they concluded is कि they have a dog. So what that Pavlov, this scientist, what they have claimed that if you have a dog, you give something to eat, okay, it will respond with salivation from his mouth, okay. So it means that that dog is very excited to have this food, okay. Okay, food is okay. Now if you ring a bell inside around that dog, he is normal because there is nothing called food in his mind. So this is very normal. Now what he has done is he told some server that whenever you are giving that dog a food, just ring a bell, okay. So whenever he came with the food, he ring a bell. Whenever he came with the food, he ring a bell. So now dog is looking at the food only, but his sensory organs are also listening this device, right. So after that, by listening only the bell, the dog can get salivation. So it's more like that if you think about it, as when we are very small, okay, and our fathers, when they came back from the office, they usually when we are very small, they usually have some small things to eat or something like that, okay. So we are very excited to see them. So at the starting, that kid is actually responding to that thing that is very delicious to that particular kid. But what he is waiting for, he is waiting just for the bike sound or the car sound or the gate sound, whether this sound happens and he get to know that something is going for him to eat, right. So it's more like this is also the part of the psychology event. So in this way the reinforcement also works. So somehow we reinforce ourselves, we connect 2 or 3 different things all together, and this is how our brain works. So basically they have actually divided some steps, or you can say some modules in reinforcement learning. So first is your agent, which has the power to take decisions or something, okay. Second is your environment, okay, in which you have some states or space. So in chess, if you are told that what move to play in a given situation, that's supervised study, okay. If it doesn't matter, it's unsupervised, it means. So if you just play win or lose or only get a reward at the end, that is called reinforcement learning. So you have to figure out which moves makes you win, which moves makes you lose. So this is how reinforcement works. So it involves one agent, okay. That agent can be your game board, your opponent, your helicopter, which interacts with the environment, okay. The agent senses the state of the environment and takes action to influence it. So for example, the agent is the board, and presently your the king is here from the chess board, okay. So what actions will the agent make that it will change the state of this particular king, okay. So the key challenge is the action must consider long term benefits. So we will move towards those, we choose those actions which will give you benefits, which will make you win, not just immediate rewards, right. That's how you learn to play chess. Chess is a very important example, in reinforcement history, because how they are making to play these games. This is more like how many moves you have, okay. So reward signal is, it can be scalar, feedback from the environment, it can be crashing, it may be -100 at, okay, you are just going to lose. So if you have played some games on your mobile phones also, some of your moves, if you don't have enough moves, it is written as you have moves left but you have no states left. So it is giving you, okay, you are now going to be, lose this game even if you have 5 moves left in Candy Crush or so, because no other options are there to make you win, right. So this is how they are predicting it, okay. Now whether this action will makes you lose this game at the instant, this action will make you lose the game in, let's say you have a Candy Crush problem, right, in which you have to make some matches. So you have to move your blocks here and there. So you have made one decision and moved the blocks from one place to another. Now you need at least 5 moves to come back from this situation, but you only left with 2 moves. That's why sometimes that games end before your moves end. You don't have much moves left. right? So this is how the prediction works. This is how this reinforcement learning becomes comes into picture. So it's more like the biological analogy that rewards and punishments are interpreted from sensory inputs. So for example, someone is giving me output, oh very good, you are doing a good job, or saying, okay, what have you done, are you lost your mind? So these are the things that we are receiving from the sensory inputs from as a human body, but in games or in reinforcement learning tasks we have some other sensory inputs, right? So that there is one type of learning that is temporal difference. It means that we don't predict the actual final state. So what we are going to how we are calculating it, we predict the future rewards by updating estimates based on the later predictions. So it's more like that, predict at time t plus 1 is more accurate than time t. For example, you are playing chess, you make one move, okay, you don't know how it will affect at the end, but as you move forward, if you are making more and more and more moves, you should be more and more and more smarter. Maybe you have making a wrong choice at the starting, but your prediction should be more accurate as the time goes on. So this is called as temporal difference, okay. So chess confidence in winning increase as the game progress. So it means that as the game moves on, the chances of winning should be increased. So update rule is more like that, adjust the earlier prediction using newer information. So what you have done, what you have already been performed, just update some values for that, okay. So there is one problem for it, wait a minute. This one. So let's say this is our game where you have to start here, okay. So when you start here, obviously you need some quantification, then you can say that this is good or this is bad, okay. So they are saying if you reach here, then you will win +1, and if you are here, then you will lose -1, okay. So objective is you have to maximize the reward. It means you have to go from this state to this state, how to move ultimately, all right. So for each state, what they are saying, they are defining a variable that will store its value. The value of the state will help you to determine whether you are moving towards reward or punishment. So how the value is defined, they are saying the value at winning position is +1, the value as losing position is -1. So you have two chances, right? Either to go right or to go left. So they are saying taking the maximum value of these two states and multiplying it by -9, they are defining this value of any state, okay. So how they are defining these state values? So question is, by using these state values we can define our whole problem, okay. How? So they are asking you the first question, what is the value of x4 after one application of the given formula, okay. So how you are going to say it? You are here, okay. Value of x4 means you are here, and how to calculate the value? This is your +1, this is your 0, okay. Otherwise all the value of a state is initially all the value of a state is 0, and if you are here, what will be its value? You have to calculate. So what there are two possibility, either go right or go left. So 0, 1, the maximum of this is 1, okay. Multiply it by 0.9, so answer will be 0.9. So why I am choosing x4? Because it is near to my reward. So I am going towards, I am starting the problem from the back. So this is your main reward, you don't know anything, just update before its state, update before it is state, update before it is state. It's more like that. If a maze problem is there, you are sitting here and there is some maze and you have to cross a path and reach here, okay. So the weights updation should be more like, because it's where to reach, just start it from here and make a path, you can easily get that path, right. So similarly, in the way when we are going to calculate these values, we start with the highest value rate. We don't know anything, we can have the dead end. So basically we are choosing this and moving towards backward. So that's how they are calculating the value of x4. Similarly, if they ask you the value of x1, this x1, so it means that similarly same question, it is 0. x1, if you are here, then there are two chances, this and this, minus 1 and 0. What is the maximum value? 0. Multiply it by 0.9, that is again 0. So it will be giving you 0. Okay, so this is how the value of a state is calculated. So using these value of a state, you can choose whether to go left or right, and you have to update all these values, because this is a
Ma'am, could you
snapshot.
repeat this problem once again, please? This problem I did not understand.
This one, seventh problem or whole
Yes,
problem?
yes. No, seventh one.
So basically the question was asked, what if you are at x1, what is the value of this state, this node. So the process to calculate the value is check left and right, take the maximum value. So it is minus 1, it is 0, the maximum is 0, and multiply by 0.9. So it will again be 0. So the state value will be here, will be 0 only.
But it will have moved to x2, no?
Yes, it will move to x2. It will move to x2. Look, this is more like, it's more like this question is about, you are here, then you have to calculate value. But if you will start from starting, the whole values are 0. Okay, if you are going to be here, okay, if you are going to be here, and you have to update all these weights. So let's say from one iteration, because all values are 0, you start with this point. Maybe you have chosen the wrong way. When you reach here, okay, then ultimately the nodes which you have explored, you have to backtrack them and update their values. This is how you learn from this. Okay, so how this chess is trained, how these games are trained, many of the moves are being given in vain. It's mean many bad moves were made. So from those bad moves, the system, the model has learned, okay, this is not a good way, update the weights. This is not a good way, update the weights. This is not a good way,
This
update
is
the
the
weights.
TD learning algorithm.
This is the concept of TD learning. Means whole concept is not given in these lectures properly. So this is the concept. It's a very simple concept where you are saying that at each step you have to be improving. Okay.
Okay.
So that's why it is written like, what is the value of state 1, x1, after one application of given formula. One application means, it means that all the values are 0, and here it is plus 1 and here it is minus 1 in the initial state, if you are at this state or this state or this state. Next question is, what is the value of x1 after v converges? So v converges means you have found the final path, exact path, and you know the exact path right now. So if you know the exact path, it means that this is plus 1 state. So from this plus 1, I will channel it out backwards. So here, from here, I decide what is the value of this node. So this node will be more or like this. This is 0, this is 1, this will be 0.9. Okay, now I'll update this node. So this is 0, this is 0.9, the maximum is 0.9, 0.9 into 0.9, this is 0.9 square. Okay, so now I'll update this state. So it will be 0.9 cube. It will be
Now, how did you get those numbers actually, from which equation?
This 0.9, the initial question it is written. It is written here ki these values
Okay.
are okay. So this is like value function in which we are saying that this policy is already being made. So this is more like, it's called a policy. This is how you are moving. So ultimately the learning is in the same process. You have defined some method, you are going towards the end state, which is your goal state. But now the learning is not like gradient descent. The learning is like which moves will making me to go towards that state. Okay, it's not reinforcement learning is not for those regression tasks. You have to, go towards like getting the value of 1 or 4 or 5. No, it's more of like a complicated task in which you wanted to find out that from this state what action is important, what decision is important. So there are multiple methods. So here we have not even started reinforcement learning, start bhi nahi kiya hai, because it's a typical concept, it's way too much. It's a simple example given to you so that you can have an idea that how this reinforcement looks like. All right. So this is all for today's class. So we'll meet tomorrow also, and I got some feedbacks from you. I'll be including those assignments. Someone has mailed me, so I'll discuss that assignment tomorrow. Someone has written in the feedback, I think 9th or 10th assignment, I don't remember. I'll discuss that also in tomorrow's class. One of you have told me that to again repeat the back propagation numericals. I'll go through them. Secondly, someone has told me to have a rough sketch of some initial numericals. Okay, we will keep them. Majorly, I'll try to give you some intuitions with the help of coding also tomorrow. So tomorrow's lecture, till now I have this in mind to discuss it with you, but still it's something.
Will you take another session regarding tomorrow? After,
Sorry.
ma'am, will you take another session except tomorrow?
No, tomorrow will be the last class for this
Okay,
course.
on same time.
Same time, 6 to 8.
Okay.
Okay.
Madam, if possible, summarize from beginning to end, madam.
Okay, I'll try it.
In
Yes,
short.
ma'am. Yes.
In
Yes,
short.
sure. And
Thank you.
secondly, I want to give you some. Actually, there is, if you are interested, if someone in your institutions or if someone in your known is interested, we are organizing one challenge for ACM this time. I'll share this to you. Okay, so you can try it if or someone you know can help you for that, it's good. So it's more like it's GROMO 25. We are organizing this challenge with one of the topmost conferences in our field, ACM Multimedia. So here there are 2 tasks. So we are giving you this data, already data is given to you, and you have to make an algorithm which can count the number of leaves and which can predict the age of these plant. Okay.
Ma'am,
So
repeat problem statement.
problem statement is some data is given to you. Okay, data will be given to you as these images. So you can see the images, right? So there are 4 types of plants and there are 2 tasks to do. So first, this age prediction, you have to predict the age. Second is the count of leaf. But the challenge here is you have to use multi-view data. It means we have data, if you can see here, this data is collected from all the views, 360-degree view. Okay, so we have rotated our camera and capture the image of this spot from all the directions. So our challenge is to use this multi-view data. You can use any type of data, any type of multiple images to perform these 2 tasks. Okay, these 2 tasks we have used deep learning, and for that we have one code also. All right, so GitHub and paper is already provided, which we have solved it. We have have some model, we have accuracy, we have basically errors for this. So it's like, this is more like baseline given to you. You have to beat it. So ultimately you have to beat this. So this is our paper. You can go through that. I have given you this link in your chat box. And you can take help from anyone, but if you want to participate, just go through this site. We have a registration link. Register yourself and try to participate in this challenge. And there is no limitation for your number of members. If someone you know who is good at machine learning or deep learning, take help from them, no worries. If you are able to beat us and come in the top 3, okay, so top 3 papers are going to be published there. So if you know someone, you can pass this information to them also. It's a good opportunity. Even if you don't know, I would suggest you to think about to see these challenges, so that you can have an idea that how things are happening in, you know, real world or with
Ma'am, it is offline or online?
this is like offline. You have to complete it at your end. You have to submit it, and then we will check on this website also. We will create a leaderboard. Okay, so if you are in the top 3, then we will ask you to submit a paper, and that will be published in ACM Multimedia. So it's more like, but yes, it needs high competition power. That's what I wanted to tell you beforehand, that it takes high competition power because data set is very large, but you can start at least seeing these things, these are happening outside, you know, in the world. So there are multiple challenges.
Any deadline, ma'am? Any deadline?
Yeah, deadlines and everything is given in this site. Okay, so basically
Okay.
these are the
Okay, ma'am.
selection deadlines. So basically your testing phase will start by 30th April. So we will share you will share our model with us. We will test it and give you one, you know, ranking. Many teams have been participating in this competition, so we will be giving the top 10 names or so that you can have an idea that where you are lying. So top 3 will be if you are going to submit your paper, and top 3 will be presenting it in this conference. The ACM link is also given maybe here. I'll share this ACM also, so you can have an idea what I'm talking about. So it has no fees. First of all, it does not have fees. After submitting it, you can be invited there, but that's why I am telling you, if you know someone who know about something about machine learning or deep learning, you can share with them. You can ask them to be in your team. It means it's a team work, and you don't have to come anywhere. You just have to work at home, just submit it, and you know. All right, so this is what I wanted to tell you. Thank you so much for these sessions, and
Yeah, ma'am.
Ma'am, one doubt.
Tomorrow session is a coding session होगा मैम.
not coding, but some of you have told me you have some assignment questions which require some code. Okay, so we'll
Yes,
discuss
ma'am.
that.
Yes, ma'am.
Ma'am, I
Ma'am,
have
actually,
some.
Ma'am,
Yes. Who's
ma'am, can I speak?
who is speaking? Just raise
Ma'am?
hand. I'm not able. Iyer, right?
Ma'am, when we have to start the research paper which you discussed just now, sorry for the asking this silly question, but we have to submit in which mail ID, ma'am?
Okay, no mail ID. This is what the information will be given to you because the testing phase will start by 30th April. Before that, we will mail you everything.
Okay, ma'am.
So the registration link include one email ID of the corresponding person. So you can.
Ma'am, first we need to register it first, or we have to start writing research paper
No,
directly?
this is not about research paper. First, you have to complete this task.
Okay.
Create models. Okay, register
Okay.
it first. registration means one simple form, Google form is there, you just have to fill it your information
Okay.
and start working on these tasks. We will share you the details by maybe in by the next week if you are going to register it in this by this week. So what are the guidelines? You have to submit it. Research paper, we will be asking for those who will be in the top 3.
Okay, ma'am.
Okay, so we need your results.
Ma'am, still we can present the research paper, ma'am, which we are doing right now, which you shared the task in the form of task. We have to send according to the dates given, accordingly,
Yes,
separate.
yes, you have to provide your models to us. We will test it. We will give you one leaderboard on the website that
Okay,
these
ma'am.
teams are in the top 5 or top 6 or top 3.
Ma'am,
So, yes.
sorry for the interruption. I have to include in the team, or it is we can do it individually. What is your suggestion in the regarding what the task which is given right now?
I would say if look, it's upon your capability. If you have good computing power, if you have good resources, then you are, alone
Can
are
we
enough.
include two, three person with me? It is fine, or what is
Yeah.
your opinion
No.
about it? So sorry
Actually,
for the interruption.
no, 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 no. I think you should go with the team.
Which
Because
team I
because
should include?
because task is heavy. That's why I told you first that contact those person who have some idea of machine learning and has good computing power.
Ma'am, it should be very good understanding should be there, no? So that to include him because the time is very less. We have a 26th, our exam is there. So in
Oh,
that critical time, we have to complete the task which is
wait, wait,
scheduled.
wait, 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 wait. This is not related to this course. I'm sorry. I should be very
Okay,
clear.
ma'am. Okay, ma'am.
This is not related to your course. This is what where I am from IIT Ropar. We are. This is an
Okay,
additional
ma'am.
thing that we are organizing. That's why I wanted to share it with you all. That you can try looking out these terms. If you don't want to participate, is okay.
No, ma'am, we
Basic.
can still try.
Yeah,
So
you
it
can
will
try.
be an
Uh,
opportunity for us, no?
yeah, it will be good for your future. It's not related to this NPTEL course at all.
Okay, ma'am.
Someone else, Himanshu, yes.
Yes, ma'am. Ma'am, I have a few doubts about a decision tree topic.
Okay,
Week 7 wicket.
okay, can we go through this tomorrow because I have somewhere
Okay,
to
okay,
go,
ma'am. Okay,
right? So we can take
okay,
your
ma'am.
doubts tomorrow. Okay, Shweta.
Okay.
Actually, today, regarding the policy-based and value-based learning, no, for reinforcement learning, and the TD learning, can you just tell which one is which? I did not get that correct picture of it.
Actually, it's not about policy based and value based. I'm not, working in reinforcement learning. To maybe currently, I am not able to give you the exact
No,
difference.
we don't have to study that for the exam, no? That policy-based or, I mean, whether TD learning comes under this or that, all that we don't have to know, no? For the exam, it's not
Look,
required,
if
no?
it is in the videos, I have not seen the videos of these, reinforcement. I have not gone through the SIR's videos presently, word by word. So if it is present there, you have to look out that. If it is not there, then you can skip it somehow.
Okay.
Okay.
I have
Okay.
two more doubts. I'll ask you tomorrow then. It's fine.
Okay. Okay.
Okay.
Okay. Okay.
Okay.
Okay. Thank you. Thank you so much.
Thank you.
Okay.
Thank you so much, ma'am, for
Thank
your
you so much, ma'am.
Thank you. Thank you.
the queries discussed, doubts.
Hello. Okay. All right. So we'll meet you tomorrow.
Thank you, ma'am.
Thank you. Thank you
Tomorrow.
so much.
Thank you, ma'am.